Let's take a look at the chain rule. The chain rule is going to be one of the more complex derivative rules. It's going to take us a little bit of time, but once we get the hang of it, we just got to be careful and it's really not too bad. The chain rule tells us if f and g are both differentiable, the derivative of f of g of x is equal to the derivative of f, leave inside the g of x, the inner function the same, times the derivative of the inner function. So again, to say that another way, take the derivative of the outer function of leaving the inside alone times derivative of the inner function. So let's take a nice simple example to start off with. Sine of x squared. And we want to find the derivative of this. So let me stick the dx operator in front. We need to know what we're trying to do with the problem. So I want to take the derivative of this sine of x squared. We should know what the derivative of our trig functions are. So we see the sine, and we know the derivative of sine is cosine. And I'm going to leave the inner function, the x squared, exactly how it was. But now I'm going to take the derivative of that inner function, and the derivative of x squared is 2x. And it's common practice to bring those variables and constants to the front. But that would be our answer. And really the thing above it is correct, just kind of written in a different format. So this is going to make our lives easier in a lot of ways. For one, we now know how to find derivatives of things like this, but two, even problems that we just didn't want to have to work out before. So for instance, if we were to take 5x squared minus 2x plus 1 to the 9th power, and I want to find its derivative. Well, we could have solved this before, but that would have required us to multiply this thing out 9 times over. We couldn't take its derivative right away. We would have had to simplify this first. And there's no way I'm about to multiply this thing together 9 times over. I just don't need to do that. So the chain rule tells me, hey, I can treat this exponent as the outer function, so I have something raised to the 9th power. Well, I know how the power rule works. That 9 comes to the front. Chain rule tells me leave everything inside the same, leave the inner function alone, and take that power and reduce it by 1. So we've taken the derivative of the outer function. And now I'm going to take the derivative of the inner function. So I'm going to ignore this 9 entirely and just look at the 5x squared minus 2x plus 1. The derivative of 5x squared is 10x. The derivative of 2x is minus 2, and then the derivative of 1 is just 0. And again, I'm not going to multiply this thing together. There's just no good reason to. And so it's taken a very complex problem that would have taken us forever to do before and turned it into just a one-line problem. Now we can combine this chain rule within other rules too. So let's take the derivative of 5x to the 5th e to the 2x squared plus 3x. So we can see here that we have a product of two things. We have this 5x to the 5th, and really the 5 is just a constant multiple. If we went to pull it to the front, we could. And we have this e term. So we're going to have to use the product rule, but within that product rule, we can see we have quite a complex chain rule here too. Really not too bad. So I'm going to start with the product rule. The product rule says leave the first term. So the 5x to the 5th will stay. Then I have to take the derivative of this second, not term, but a factor, second factor. So I'm going to leave the e to the 2x squared plus 3x because I know the derivative of e is just itself. So if I take the derivative of the e, it's just itself, but then I also have to take the derivative of that inner function, and the derivative of that inner function is 4x plus 3. Now I'm halfway there. This is the derivative of the second. I left the first. Now I'm going to leave the second, so I'm going to leave the e to the 2x squared plus 3x. I'm going to take the derivative of the first, and the derivative of 5x to the 5th, 25x to the 4th. Now, always read what the problem wants, but for these sorts of problems that there are a lot of pieces, a lot of terms, a lot of factors, I won't always ask you to simplify those. I'm looking to see, did we get the right idea with the derivative? If not, can we simplify numbers down to very nice small numbers? So we saw early on in earlier videos when we were doing just the basic rules, a lot of times it's really nice to simplify because it made the problem easier for us at the start. There's no way to simplify this, and so I'm not going to bother to simplify this final answer. Now, again, there might be times when I change my mind on that, so always read the problem carefully. Let's take the derivative of cosine 2x squared plus 1 over the square root of 9x. Well, here we have a quotient, obviously, but then within that quotient we have some chains that we're going to have to do. We have something inside that case and we have something inside that square root. The first thing I need to do with my quotient rule is I'm going to just write the denominator. And then I'm going to take the derivative of the numerator. So the derivative of cosine is a negative sign. And the chain rule tells me to leave the inner function alone. So the 2x squared plus 1 will stay. But then I have to multiply by the derivative of the inside, which is 4x. And the derivative of 1 is just 0. And then I'm going to subtract from that. I'm going to leave the cosine the same this time. The upper function is going to stay the same. And the 9x, I have to take the derivative of 9x. Well, 9x under the square root is really the same as the 1/2 power, so I'm going to pull the 1/2 to the front. The 9x is now going to be raised to the negative 1/2 power. And I still have to take the derivative of the inside, which is 9. And this whole thing is over. 9x under the square root squared, which cancels, just leaving me a 9x. Now, a little bit of simplification we could do here if we wanted to. So this 9x here is really in the denominator of the numerator. We never really like to leave negative exponents, especially when terms are matching. So I'm going to multiply 9x to the 1/2 to every single term. And so when we multiply it to the first term, we get a 9x. I can pull that negative to the front. Let me change that a little bit still. So I'm multiplying 9x, square root of 9x to every single term. That gives me a 9x, but then I also have a negative and a 4x. So that'll be a negative 36x squared. And we have the sign still there, the 2x squared plus 1. Nothing we can do with that. It's on the inside. Remember, we can't multiply to the inside the signs. Minus, and then here we just multiplied by the square root of 9x, so that'll cancel because it was in the denominator. We have the 9/2 as our coefficient on the cosine of 2x squared plus 1. And we had a 9x in the denominator, but we just multiplied it by the square root. So this will now be 9x to the 3/2, like so. I also see that I can divide a 9 into everything. So again, if we want to simplify, we could do that pretty easily, giving us a negative 4x squared sine 2x squared plus 1 minus 1/2 cosine 2x squared plus 1. And really I could multiply that 1/2 out of there too. But I'm gonna leave it there for now. I think that's good enough for now. Let's take a look at another one. So we can apply the chain rule as many times as we would like. We can have chain rules within chain rules. So let's take sine of the square root of 3x squared plus e to the 5x. So we have quite a bit going on here. We have the outer function sine, but then as soon as we get inside that sine, we see we have a square root function. There's things inside that square root. So there's a second outer function, or really the next inner function. And then within that square root, there's more stuff. So we're going to have to apply the chain rule multiple times here. And even that inner function there, the e to the 5x, that has a chain that we're going to have to apply too. So we're going to take it one step at a time. And the chain rule says, well, we take the derivative of the outer function. We already said the derivative sign is cosine. And everything on the inside stays exactly as it was. Now, I ignore that outer function. So I'm going to ignore the signs over there. I'm only looking at what's in the parentheses. I'm going to take the derivative of this inner function. Well, it's a square root, so we're going to have a 1/2 power comes to the front. The stuff on the inside of that square root stays exactly the same. But the exponent's going to switch to a negative 1/2 because we have to subtract 1. Now we finished with the square root, so I'm going to ignore the square root. I'm only going to concentrate what's on the inside. Well, I'm going to multiply once again. So if I look at the inner function, well, the derivative of 3x squared is 6x. And then the derivative of, we have a sum rule, so we're going to have to add. Then the derivative of e to the 5x, well, e always looks the same, but then we also have the inner function there, has a 5 attached to it. And so we really have a 5e to the 5x. And there it is. It's just a chain of factors now. We have our outer cosine, we have the square root, and then we have the stuff inside the square root. Let's mix some chain rules in with some more product rules and look at some more multi-step problems. So let's say we have 3 tangent of 5x minus 1 e to the sine x, and then we'll have an x to the 5 x to the 5th. So we have 1, 2, 3 different products in this case, and within those products we have some more chains. So we're going to have to apply product rule, and then within those product rule we're going to have some chain rules as well. Now the first thing I'm going to do is the product rule works for 2 different products, so one thing times one other thing, and right now I have 3 things. So I'm going to start by grouping these, and it really doesn't matter as long as I get to 2 products. So I'm going to choose just to group the front 2, and then the x to the 5th is on its own. I could have also, if I had wanted to, grouped the e with the x to the 5th. It really doesn't matter as long as I have 2 terms, 2 factors, and then 1 factor, giving me 2 different total factors. So I'm going to apply my product rule, and my product rule says we take the first one and we leave it alone. So the first blue bracket here, the 3 tangent of 5x minus 1 e to the sine x. I haven't changed anything there, but I'm going to take the derivative of x to the 5th, and that would be 5x to the 4th. That was very easy. Then I'm going to add to it. Well, now I'm going to leave the second product, but I'm going to take the derivative of the first. This is where it's going to be a little bit messier, because now if I'm going to take the derivative of this first bracket, that is in turn going to require a product rule. So I'm going to put a parenthesis down, because everything behind this parenthesis is going to be the product of this half, which in turn is going to require a product rule. So once again, if I look at this blue bracket, I'm going to leave the first term. So the 3 tangent of 5x minus 1 is going to stay. Nothing changed there. I'm going to take the derivative of e sine x. The derivative of e, we always have itself, times the derivative of the inner function. The derivative of sine is cosine. And then we're going to add to that. We just left the first, so now we're going to leave the second. We're going to leave the e sine x. And now I'm going to multiply that by the derivative of the first. Remember, the first is the 3 tangent of 5x minus 1. So we'll have 3 times the derivative of tangent, which is secant squared of the 5x minus 1. But then I also have to multiply that by the inner function, its derivative, which is 5. And so there we have it. So we can see that this derivative of the first 2 products is significantly longer than when we did the first. But that whole answer there would be our entire answer, that whole thing. So the chain rule, they can get more complex the more pieces we see. Obviously, there's going to be more complexity. We can have chain rules within chain rules. These give you a few quick examples just to get you on the right track.